see we can together without any obstacle here in healthy condition. Welcome to the guest lecture by Division of Veterinary Public Health with the topic Heavy Metalloid Pollution and Health Risk Assessment in Peri-Urban Agricultural Area in Developing Cities. I am Igede Disputra as Master of Ceremony will lead this today's event. But before we jump right to the lecture, let's take a picture first. For the operator, please help me to take the screenshot for all of us. And all the participants, please turn your camera on. Maybe for the operator, please help me to take a picture. Okay, let me count down for the first slide. 1, 2, 3. Okay, the next slide. 1, 2, 3. The next slide. 1, 2, 3. Okay, the last slide. 1, 2, 3. Okay, thank you so much for the operator. The next agenda is the main agenda of this event, is the guest lectures. For the agenda will be led by our moderator, which is Dr. Dadi. But before that, let me show you the curriculum vitae of Dr. Dadi first. For the operator, please share the curriculum vitae of Dr. Dadi. Dr. Dadi Raharjo, DVM Magister of Health. He was born in Kediri, September 15 and on 1961. Dr. Dadi Raharjo is the head of our Division of Veterinary Public Health and Faculty of Veterinary Medicine, Erlangen University. At 1986, he finished his Doctor of Veterinary Medicine in Faculty of Veterinary Medicine, Erlangen University. At 2000, he finished his Master of Health program in Erlangen University. And at 2012, he finished his doctoral program in Erlangen University. The research area of Dr. Dadi is in veterinary public health with 19 papers Scopus Index publication. Okay, that is Dr. Dadi's curriculum vitae. So now for Dr. Dadi, the time is yours to lead this event. For Dr. Dadi, the time is yours.
Okay, thank you very much. I'm Gede, I don't know. Okay, thank you very much. So, welcome, Dr. Pham. So, sorry I don't have your curriculum vitae, but I think you already have many works in this area. I heard from Windra for many things. So, I think is now we start in the lecture and then we can discuss for next, and then we can just not so formality, but we can how to make some of the new technology, new of the science of knowledge, and then so how we can make some works together. So I think I invite Dr. Pham to make some time for yours. So please, Dr. Pham.
Okay, thank you for your introductions. And sorry, the link I sent in the chat box is the wrong file. I will send again after maybe 1 or 2 minutes. Okay, got it. So sorry, I will send again just 1 minute now. Maybe you can get it in the chat box again. Okay. Okay, so let me start sharing the screen. Can I share screen now? You see the screen? Okay. You see the screen now? Dr. Dan, can you see the my sharing screen?
Yeah. So please.
Okay. Let's come.
Yeah.
So, let's start the full screen sharing. Maybe
Kultam. Orang Jepang lagi yang ngomong.
so it's okay. You can see my full screen sharing.
Yeah. Okay. We can see that clearly.
Okay. Thank you. So I can stop. So maybe now. Okay. Good morning, everyone. Doctor and students. And my name is Pham Viet Jung. My name, you can call me Jung or Pham. It's okay. And now I'm working as an assistant professor in a graduate school of engineering at the University of Tokyo. And I just moved from Yamata University to this university last year to start a new laboratories about reusing in municipal wastewater for agriculture and aquaculture. And thank you again for having me today. And about so I was graduated in Vietnam, Vietnam National University, Hanoi. Some brief of me in 2008, and I start studying in Japan from 2009 with a sandwich master program at Okayama University, and I finished my PhD degrees in agriculture in Hokkaido University. So after that, I have working experience in Vietnam Japan University, a new university in Hanoi National University for 2 years. And from 2017, I became an assistant professor in Yamata University, and I just came to the University of Tokyo last year. And my research interest is my bachelor's background is soil science. So I did the research on interaction and absorption or desorption of nutrients like phosphate in some colloidal particle, the small particle in tropical soil in Vietnam. And after moving to Yamata University, I also work in the risk assessment in food, vegetable, and also water in the urban and rural environment in some project in this university. And now I'm trying to develop a new system to reduce the potential resources in municipal sewerage system in Tokyo. So if you have interest in and want to talk about this kind of topic, you can email me or to have further discussion. And yeah, and now the content today, we will talk about, maybe you are not, we are not same field, so I will talk something at first about the environmental pollution in developing countries, and the next is about the heavy metal pollution in the food system and human health risk and assessment in the third session. And the last one is the main content is I would like to introduce some research on heavy metal pollution in the system, the water, soil, and food system. That's I was doing in Cambodia, Vietnam, and Thailand. And the final one is general conclusion and discussion so far. So the first one is environmental pollution in developing city. So as you know, this topic is a big issue for most developing countries in the world at present. It's called its effect on GDP, the health system of society, and also is called the death and disability for human being. And as you know, the pollution can come from many kinds of it can come from soil pollution, water pollution, air pollution, noise pollution, and also from solid waste. And also now we also hear from about the radioactive pollution, like maybe you may know the big earthquake in Japan from 2011, right? So from that earthquake, the huge amount of cesium released, that is the radioactive element released to the soil, and the soil have the characteristic in Japanese soil, like andosol soil, can absorb strongly this kind of radioactive cesium, and it remain in soil for at least 50 years after the accident. So that is the new, not new, but the new concern, not new topic, but new concerns for the local government, how to treat not only the water, wastewater from the industrial sector, but also the soil from the agricultural activity. So these pollution can be affected by many factors like rapid industrialization or urbanization. That's also happened in your country, right? In Java, Iceland, as we discussed before this lecture, and also climate change. Climate change can have the direct and indirect effect on this kind of pollution. It can enhance the frequency, quantities of the pollution. For example, this can cause a natural disaster will be more serious, more strong, like rainfall or acid rain. So it can cause soil pollution and water pollution, and so soil erosion, and so from the human mismanagement, and it will cause environmental pollution or environmental degradation. So the left-hand side figure show the risk factor and cause of global estimate that by factor. And so when you see here, you can see the total pollution here. It means environmental pollution is occupies the most of that, and in at worldwide scale. And inside this one, you can see air pollution and water pollution cause the most death. And in the top 10 countries with highest number of deaths due to pollution, we can see in the top 5 or top 6, Indonesia also in top 6 of this. They either place have a lot of death due to the pollution. And one thing interesting thing here, the pollution can come from traditional pollutants or modern pollutants. And in the current trending is the modern pollutant increasing. So that is one point we should pay attention, and it's attract many research on us. So the solution for this problem, you may know about the SDG, right? We have to implement the SDG. The SDGs it means the Sustainable Development Goal at global scale. And so from this, to do this goal, we have many pollution when we solution for this. So I just summarize here for your reference. Just the first one is advanced. We need advanced technologies, and the next one is energies, creation or conservation, or energy renewable. We should discover more and more renewable energy, or source reuse and recycle, emission trading scheme. You may know about this to reduce the greenhouse gas emission, and some policy integration, education, deforestation, so on. There are many solutions we should do, and one of that is we should take care about the environment, not only for the economic development, but also now we should develop with care of environmental protection. So the second part is the heavy metal pollution in water, soil, food system. So here, you may know about the heavy metal, right? This is the element, chemical element, have an atomic number written 20, right in this slide. And some heavy metal you may know, like chromium, manganese, or here is copper, zinc, cadmium, or lead. And some rare to know, here is metal ore, is arsenic or selenic, like this. And the property of this heavy metal, they can have in everywhere, ubiquitous assistant in the environment. And some heavy metal are essential for plant, but some are not, like micronutrients, like copper, iron, zinc, nickel for plant growth, metabolism, and development. But some with very small amount, just in trace level, are not required by plant, like cadmium, lead, chrome, mercury, aluminum, and somehow. And these trace amount have a toxic nature, even at minor quantity. And these trace element not be metabolized. It's very persistent and non-biodegradable. And the most important information about heavy metal here is they can go into the body, the organism body, by many pathways, like food, water we drink, food we consume, the air we breathe every day, and even the skin contact. So there are many risks from the heavy metal. And why is the heavy metal have just toxic toxicity because they can make a covalent bond with organic group. So by this kind of bond, the covalent bond is very easy to be occurred in the body of organism. So they can form the lipophilic ion or lipophilic compounds. This can be dissolved easily in the lipid, like that. And it can bind to the non-metallic element of cellular macromolecule. For example, it's a binding of lead and mercury to sulfide group of the protein. And therefore, four ways to enter the human from the heavy metal by ingestion when we consume contaminated food, or inhalation, we breathe in the atmosphere, or drinking the contaminated water, skin contact from agricultural chemical, or if you live in near some industrial enterprise, they can emit. You can contact some gas emission, the contaminated by your skin. And also the last one here is heavy metal bioaccumulation can cause biological and physiological complications, like its effect on cellular organelles or components of the cell. And they can interact with DNA and nuclear protein and causing the damage for this particle. So in the figure, you can see the heavy metal source pathway and human exposure. I don't go detail for this, but you can refer it. And the heavy metal can have the impact on human health. So like I just give here some example. So like some trace element like cadmium here, they can impact on your bone, liver, kidney, lung, also brain also, and your immunological. So there are many ways and many kind of your organism can be impacted by heavy metal. So in high dose of this metal, after entering your human body, they can disturb the metabolomic and contributing the morbidity or even mortality. It means it can cause the chronic effect or acute effect for the human body. For the heavy metal source, so basically it's divided into the non-anthropogenic and anthropogenic source. So the anthropogenic source means it's from human activity, like industrial activity, agricultural production, domestic wastewater or waste, etc. And the non-anthropogenic is come from nature, like rock, weathering rock, volcanic eruption, soil erosion, dust particles from wind, sea spray, aerosol. So you can see here, some source is the point source and some is non-point source. The point source like industrial chimney, you can define the source and you can define the emission point and to treat at the source. But some you cannot define it, like in natural source or even in agricultural source. Yes, discharge to the water body and yes, go to the environment with non-point detection. So from this source, many kind of heavy metal like gas, liquid, solids discharge from this source, and it's called soil contamination or sediment contamination in the water body, and it can affect on the soil ecosystem and also water pollution causes. And from that result, it can result in the bioaccumulation of heavy metal in crop or human, and it may cause the health risk for the human. And this also have many kind of source of heavy metal we can find in the literature, lies from fertilizers. The people, the growth of population make give this is requirement for more food for more people. So the use of fertilizer, pesticides, and even some biosolids manure compost will be used all over the world. So in this kind of agricultural chemical, this contain many kind of heavy metal. And nowadays, from the urbanization, we have wastewater. Many kind of wastewater here. We can have industrial wastewater and also domestic wastewater, and it's contain a lot of heavy metal. And also we have the atmospheric depositions from the industrial chimney, from mining, metal smelting, and many kind of manufacturing processes. And even though in transportation, there are many research on transportation is emit gas and also dust containing heavy metal, and it causes contamination in the surrounding area of that transportation route. In the developed countries, the wastewater treatment is a big problem now, and most of waste from the human activities were burned, have been burned now, and it have many kind of heavy metal too. This also some detail of mining, refinery process, and manufacturing. So the phase of heavy metal, basically I just summarize in this source by emission, transportation, smelting, burning, many kind of human activity, and also the natural process like watering is we release. It contains the heavy metal and it can release to the environment, and it will be dispersed by air, or it will be realized by water, and it will accumulate in soil or sediment. So from soil, sediment, and somehow water can be the secondary source for the aquatic organism or the vegetable. They can absorb heavy metal in very low concentration but toxic, and they will be bioaccumulated in food. And from food chains, due to food chain, it go into the human, and it's called health risk. So let's talk about the human health risk from heavy metal pollution and its assessment. We know about risks, right? The heavy metal I tell in some slide, but we don't know now. We don't know how to assess it, how to do it in quantitative way. So first is how can we clarify the risks and hazards. So here I just copy from the Congressional Commission on Risk Assessment and Risk Management in US. So they define risk the probability that a substance or situation could produce harm under specified conditions. Like you can see in this picture, right? Risk is mean the likelihood of the hazards causing the harm. So the risk is a probability, but the hazard is determined by the whether a particular substance or situation has the potential to cause harmful effect. So here, the hazard is something that has the potential to harm you only. It's not direct, not harm you yet, but we can have many hazards in your life. Like when you get on the motorbike, there is the hazard where if the accident will be occurs, or the hazards when you don't bring your helmet, something like that. But it's not the probability. If you want to know how many percent or the probability of that hazard can harm you, it will become a risk. Can understand like that. So on the in autumn, risk doesn't exist if the exposure to a harmful substance or situation does not or will not occur. So when in this figure, so when the hazards increase, there are many hazards outside. It can increase the frequency of the event, so it can increase the risk. So the US EPA have the step-by-step risk assessment process. So risk assessment is a method to determine the magnitude and probability of an adverse health effect from exposure to a substance. So step one, they identify the hazards. How many hazards in one in an event? And the next, they apply a dose, or they call it here a dose-response relationship. This is the risk assessment starting point. So they describe how the likelihood and severity of adverse health effect are related to the amount and condition of exposure to an agent. So step 3 is here. This step 3 and step 2 can do parallelly, is to assess the exposure. This exposure assessment is the process of measuring or estimating the magnitude, frequencies, or duration of human exposure. For example, when you live near an industrial area, industrial zones, so you have you will in step 1 you have many hazards, like you it can release the wastewater to your surrounding environment. It can emit the gas, the toxic gas from its chimney, and also the transportation surrounding that industrial zone is, I think, a lot. So it's also release. It's called many hazards. But how can we determine the dose response of the hazards, the probability? So we should define For example, if we find an event like the people have some symptom about the people living that area have some problem in the health, so maybe they will have some exposure from the contamination or pollutant from the industry zone. So we should define those response. How much of concentration of that pollutant can cause a symptom, can cause even the death, or can cause the dose can can have impact on the health. And in that case, we also define the exposure assessment. It means with that element or with that factor, how can people contact, maybe by skin or by inhalation or digestion or ingestion. So we should define that. And we also measure the concentration in the environment, and we calculate the dose response. What concentration may impact on the health. After we get that information, we will have the risk characterization step. So this step conveys the risk assessor judgment as to a nature and present or absent of threats. We will evaluate the risk after implementing the first 3 steps. That is the process. So the quantitative risk assessment can convert the environmental pollution to damage to human, and we can understand the damage which is expressed numerical at least and more easily than the pollution. Like we can create a risk map, like risk map of air pollution. It will we have the gradient of air, the concentration of some pollutant like PM 2.0, and we can make a map like that by the step from step 1 to step 3. We can do that, and QI enable us to discuss about effect of human behaviors as well as environmental factor. So when we know which exposures is the most contact is the most dangerous, we can discuss and have the strategy to avoid us. And these methods can estimate the benefits to risk reduction of various interventions like environmental cleanup, restriction of some behaviors in advance, and comparing the estimated benefits provide us with the valuable information for risk management. So this is the 4th step. So here is the calculation of quantitative risk assessment with threshold. There are many types of quantitative risk assessment. We can assess with threshold or without threshold. As you know, we don't know on threshold of on pollutants. Here I just mentioned about the chemical, the heavy metal, but we also have another pollutant like bacteria or pathogen. So in some case, we don't know its distribution, its concentration in environmental. So we don't know the threshold. So we should have a different approach to assess. But in this lecture, I just mentioned only focus on heavy metal. So in somehow we can evaluate the threshold of this kind of element. So we prefer the current research prefer to apply the quantitative risk assessment with threshold. So this equation just so you can calculate the tolerable daily intake or acceptable daily intake. Is the unit is milligram per kilogram per day. This means what amount of heavy metal, for example, you consume, you can intake, you can uptake to your body in 1 kilogram of your body weight in one day. That is meaning of daily intake. And the NOAEL is in no observed adverse effect level, and low is observed adverse effect level. So this is the reference of this value can be calculated from the data. For example, if you check the data heavy metal in water in your river near your living, and you can calculate this value, and you divide it for a uncertainty factor. It means a reference factor, and we based on this we can assess the whether there is risk or not from a pollutant. Okay, so I will talk the main topic today. I will talk about some case study I did in Cambodia, in Vietnam, and in Thailand. So the first one is the assessment of heavy metal bioaccumulation and source in 6 edible fish species of Tonle Sap Lake in Cambodia. So you may know the Tonle Sap Lake is the largest freshwater and also the biggest water source for the living of local people. And it's also the water irrigation source for agricultural production in this area. And the fish from this lake is also the main food, not only for local community but also the very famous fish service in for tourist activity and also export. And in recent years, the increasing pollution of the lake with heavy metal from anthropogenic activity has been concerning, because they maybe from the medical report, some people living in this area have some symptom or some chronic symptom on their lung, so it raised a big concern, because one of the most dangerous of heavy metal is not called the acute effect but chronic effect gradually. So we cannot see it at 1 day, 2 day, tomorrow after consume a contaminated vegetable, we cannot observe it, but we can see it after a couple of years. So it is a big problem. That's why we should do the health risk assessment. So the source of heavy metal in Tonle Sap area can come from many kind of activity. Maybe it's the source can be related to many activity in this area, like transportation for tourists, for living, even from nature source like parent rock watering, and some village, some floating village, some communities living on this lake can be one of the source. And agriculture, aquaculture, chemical, fertilizer also can be a source. and it can go into sediment and aquatic organism and go to the people, the human by consumption. So the factor effect on fish heavy metal in this study, we focus on the species of fish, seasonal change, and so social change or the location to see what different between these factors. And this study to evaluate the occurrence of heavy metal in plastic tissues of different fish species collecting from different sites of tonle during dry and wet season. So here is the fish sample. Actually, it's not. I'm not so familiar with this, but this is the freshwater fish, and let me use the local name for easy understanding. So tray is meaning the fish in Cambodian language. So we have Roma, Dev, Kaman, Krang, Potuk, Slap, and you see in this six fish is the sample fish were collected in 4 sampling sites. In Siem Reap, it's quite a big city with famous tourists. And in Batabang and Kampong Thom and Kampong Chhnang, this Kampong Thom and Kampong Chhnang is quite crowded area, and it's close to the can say the downstream area of Tonle Sap catchment, and Batabang and Siem Reap is like an upstream area of the lake. And we collect at two times in wet and dry season during 2017 and 2018, and collected randomly at the 4 province with 6 species. Totally, we have around 130 fish. And the fish was after washing by clean water, we separate fish muscle. We just focus on fish muscle because this is the diet part of it. So we use the fish muscle for this study. We did not measure heavy metal in intestine of fish, and freeze drying and pulverizing the fish before analyzed. So the sample were digested by West digestion procedure, and the heavy metal here, like zinc, lead, chromium, copper, cadmium, manganese, nickel, and arsenic were determined, and the data was analyzed. So at first, this is the heavy metal concentration in fish tissue. So because we use the unit in milligram per kilogram or ppm in wet grade of fish, and you can see here the result of heavy metal concentration of heavy metal, and we compare the concentration of heavy metal will compare with the standard. This is maximum permissible limit of heavy metal in food was used to compare, and we found only the crank, the fish named crank, and somehow in this fish, Notoclitus slug fish, were contaminated with manganese and nickel. In crank fish, the contamination level is very high compared with another fish, as you see. this fish is the fish living in the bottom of the water body, so maybe they can eat slug and also the bottom part organism, so they can have a high frequency for exposure of heavy metal by their characteristic. And this result to compare the heavy metal bioaccumulation in fish by fish species. So yeah, as you know, the cranfish have significantly high like manganese, nickel, copper, arsenic concentration in the cranfish were significantly higher than those in other fish. And zinc and chrome concentration in crane also higher, except for the zinc of broma fish and Kaiman fish. It's not different in statistical analysis. And lead and cadmium, no significant difference were found here between fish species. And here is the concentration, heavy metal concentration result in fish with sampling site. So as you remember, Siem Reap and Batabang in the upper part of lake, the Chenang, Kampong Chenang and Kampong Thom in the lower part of lake. And we found the Kampong Thom were significantly higher concentration of zinc, Kampong Thom, zinc, magnesium, and chromium in fish tissues than those in the other sampling site. And lead concentration in fish tissue collected in Kampong Thom was significantly higher than that in Battambang. So there is no significant difference of nickel, cadmium, arsenic concentration in fish tissues among sampling sites. And here is fish concentration in fish relationship with us with the seasonal change. So in we only found there is a significant difference by seasonal change in zinc bioaccumulation. The rainy season, zinc in rainy season seem to be significantly higher than just in dry season. And here we try to determine the source, the potential source of fish by using PCA analysis. And by this kind of statistical analysis, we can see the how can I say the profile or the correlation between each between the element. So if the element, the heavy metal have the same direction here or here, it means they have same profile in a certain environment. They have correlation. So maybe we suggest that it may have the same source, same origin. For example, zinc, magnesium, and chrome here in upper of this line. I just remove the arsenic because this show the same trend, same correlation, positive correlation with this, but the length of arrow is not is short, and the PC here you can see in PC1. On the PC1, the arsenic show the least correlation with copper, chromium, and magnesium, nickel, and zinc. So I just omit it in this relationship in the inference discussion. So here we think that zinc, manganese, and chromium have the same origin. Like we can find this kind of element in agricultural runoff. The wastewater from agricultural activity surrounding the Tonle Sap Lake, or paint used in the boat. This is the sampling site is the lake, so they use the boat or for quite frequently for transportation. So the paint or the liquid of gasoline or the paint from the boat can be one of the source. And the magnesium and zinc and chromium also, in some literature, they say that it's from the leaching of rock. It means it's not the anthropogenic source. It's not from human activity in nature. Otherwise, lead and cadmium can be same origination. Is made from the sediment due to the industrial activity, and copper and nickel may be the same source, like from domestic wastewater or aquacultural activity or leaching from rocks. So summary for this case study is the mean concentration of manganese and nickel exceeded the standard in all species, and raising a concern about the possible health problem caused by this metal. We did not calculate the health risk assessment. We did not do the health risk assessment in this. I will show it in the next case study. But comparing with the standards is one of health risk assessment, because to have that data, the standards, I mean the NPM, most of data in the developed countries it differ from the US data. So they have the study on I mean the labo scale study. Do you remember the step 3? The step 2 is dose and response interaction. They have that experiment in laboratory scale to check with this limitation, if there is some element higher than this standard, it can cause a health problem. That's why it's just one way, and the easiest way to compare, to assess the health risk. But actually, it's different between the country by country. The consumption amount of fish in American different with Indonesian, and also different with Cambodian, based on country by country, and also based on the living environment, and also based on the gender, children and adult is different. So that's why we should calculate. It's better to calculate based on our data. But in this study, I have not do it. It have time. I will do it later. But and the next here is the fish strength have effective bioaccumulation of most of target heavy metal, and the heavy metal in fish collected at the Kompong province, so significantly higher concentration compared to other sampling sites. So except for zinc, fish heavy metal concentration were independent with seasonal change. And PCA results indicate the common origination of manganese, nickel, chromium, and zinc. Meanwhile, cadmium and lead may be the same origin. The case study 2 is a study about effect of untreated municipal wastewater on heavy metal contamination under seasonal difference and health risk assessment of vegetable growth in peri-urban farm of Phase City. This also the case study about the heavy metal pollution in area, agricultural area near a big city, development city. So as you see in this slide, it shows the sampling site, the study site, and you see Phase City is the center of Vietnam, and this is a developing city, and they have the river flow to the center of city, and it's go to this area is the agricultural area, very important place to provide food like vegetable and some aquatic organism for the city, and we will study on this site. And this city have dry season and wet season, the same with Tonle Sap Lake area. And the heavy metal contamination of farmland is also receiving many concerns in the developing countries due to the expansion of industrialization and urbanization. And the Phase City have tropical monsoon climate, and this city have not the wastewater treatment plant. So the wastewater will be discharged directly to this river from the urban area. And we hypothesize that the heavy metal in wastewater can be discharged or can be relocalized by the water, can transport by water to the downstream area, which is the agricultural production area, and it can cause a contamination in food, in water, in soil, and also in food with heavy metal. So this study aim to investigate contamination of heavy metal in irrigation water, soil, and vegetable under effect of seasonal change and untreated municipal wastewater of Phase City. And another purpose, objective, is to estimate the carcinogenic and non-carcinogenic health risk potential to local residents via vegetable consumption harvested in the area. So we can apply the quantitative health risk assessment with the threshold in this case. Yeah, this is the sampling. The sample is taken from May 2018 to April 2019, and irrigation water, agricultural soils, also non-agricultural soil, the bare soil, for example, and the leafy vegetable. Here we give these areas mainly cultivate with lecture in this time, and we select lecture as a main sample of vegetable. So we select 3 sites. This site is in the upstream area with hypothesis that no effect of heavy metal from the urban domestic wastewater. And this B side, C side, one is close to the urban area, and one is further to be compared. And at each station, soil vegetable sample were taken at least 3 different points to assemble one composite. And also treated municipal wastewater was taken. So here's I just skip here that just for this digestion process, and we also do the same procedure with case study in Cambodia, and use ICP-MS and AAS to analyze heavy metal. The health risk assessment. This is I estimate the daily intake of vegetable. So I just propose the main exposure of the local the local people is the injection injection of vegetable. No skin contact, no eye contact, and I use that hypothesis to calculate. So thus calculate by these equations. Here is the content of heavy metal C. It means the analyzed heavy metal concentration in vegetable. And we find many information from the literature, like ingestion rate in Vietnam for the adult, and conversion factor used is 0.085 in some reference, and we calculate for 1 year exposure by consumption, vegetable consumption. And the exposure duration here is we estimate that 30 years based on the average lifetime. 30 years is mean after you after your maturation, and body weight, the average body weight is around 52, right? Around 53, and average lifetime here. So for carcinogenic, it's a chronic effect. So we use 70 years from refers from previous research. And for non-carcinogenic element, we use ED, the 30 year, and unit conversion. Yeah, you can apply this to any study related to heavy metal. So we have daily intake, and now we calculate the risk. So for carcinogenic risk of a heavy metal, we multiply the daily intake with the factor. This is slope factor. So this slope factor differ from previous study for each element. Each element had the different slope factor. It shows how probability of one person to consume a certain amount of contaminated vegetable per day to exposure with the carcinogenic risk. And non-carcinogenic risk, similarly, we can calculate by these equations. We divide to RFD. This is reference of dose. The dose also is provided from a previous study from US EPA, and they think that with this dose will cause the human health symptom for a person who consumes contaminated vegetable, for example. So that's why if this is the total, that's the total of all heavy metal. This is for one heavy metal. So that's why with these two these two parameters should have to be compared with 1. If it's larger than 1, so their individual or accumulated exposure. When it happens, it will be resolved in the adverse non-cancer health effect. So the health effect. If you find this value that less than 1. And similarly, how to evaluate the carcinogenic risks? It will be compared with 10 power minus 4. It means if it's if higher or if higher than this value, it means there is more than 2 or more than 1 person have the symptom of have a risk of carcinogenic risk among 10,000 persons in the population. So that's why this standard was made. If less than that, it means among 10,000 persons, less than 1 person exposed with this risk, have this risk. It means the risk from that heavy metal can be negligible. That is the meaning. So we do some data analysis like PCA, ANOVA to compare data. It's not this one. And this is some result. So the light shows the standard, and we can see in dry season the zinc, and even in dry season and wet season the zinc so the highest concentration in water. And the order so in this slide, and cadmium had the lowest in both seasons. The on of heavy metal concentration was lower than standard. This means it's acceptable. It's okay to use. So no significant dependence of heavy metal concentration with sample size. And about the seasonal variation in this slide, you can see the lead and cadmium in dry season significantly higher than those in wet season. And I show you here is the result of PCA analysis. So the PCA not only give you the correlation between a group of element or the icon here in the analysis, we call it variable, but they also show you the group of factor. For example, this is we select factor is seasonal change and factor of sampling size, so we can see how it's correlate its order. So here you can see the overlapping, so that there is the correlation between the factor group. So the wet season so in the light blue color, and dry season so in the brown color here, and the result of a heavy metal in wastewater was shown in the blue color here, you can see. And the size C is in square, symbol of square. Size 8 is the dot. Size B is open square. And you can see in wastewater, irrigation water, the heavy metal in irrigation water here if you see, firstly, you can see the side, let me see, side A. So the side A, there's no difference between the, there's no difference of heavy metal concentration in irrigation water inside A. It's independent with the seasonal change. You can see easily. But they are different with side B and side C. This means side A in the upstream area. So the heavy metal in upstream area not change significantly during the seasonal change, but it changed in side B, side C in downstream area. So it means the river is the same. Right? So it means there is some effect from the urban area, or I mean the domestic wastewater. We can say that because the most effect, the most factor is the wastewater from urban area. Now it's clear if we do this analysis. Yeah, I just say about that. So we can see that undeniable seasonal effect of untreated municipal wastewater on heavy metal contamination in irrigation water. And the second one is the vegetable soil, heavy metal in vegetable soil. And we see the dry and wet season. We also have the same trend with the order of heavy metal concentration is quite same with water. Zinc is the highest and cadmium is lowest. And on soil, so that there's no contamination when comparing with standard. And cadmium, zinc in downstream is higher than upstream. And side B, chromium, lead, arsenic in side B larger than side A. And there is a seasonal difference of chromium, cadmium, arsenic, zinc significantly by the seasonally. Like zinc, arsenic in west larger than dry, higher than dry season. Chromium and cadmium in dry season higher than wet season. You can check it in the figure. I just summarize some comment here. And how about the PCA model? So you can see this is the wastewater, municipal wastewater. It's quite far. There no overlapping between heavy metal in wastewater and the heavy metal in soil. I mean the correlation in the variable group. Here it means heavy metal group, and the variation just of wastewater and just of soil in the sampling site. So there's no correlation. This means the impact of heavy metal in wastewater is not strong enough to change the heavy metal variation in soil. That is the meaning. And you can see also, generally the side C and side B have the same in the right hand side. This means it had quite similar correlation compared with side A. So it's again determined that there is the significant impact of seasonal change on the heavy metal concentration in soil. And how about the vegetable? Vegetable is here in dry season. We have also zinc is highest, and the lowest one is arsenic. And we have the lead, cadmium, and zinc have strong contamination. Have the strong contamination in vegetable. with lead cadmium and zinc, and cadmium and arsenic in side B also confirmed larger than side A. And all heavy metal have different significantly in seasonal change. The wet season is higher than dry season. And how about PCA result? As you see that here, yeah, it's quite the same with the numerical result here. The wet season have different behavior. I mean, the not overlapping with the dry season in here. And in the wet season, there is a correlation between the wet season, how can I say, the heavy metal in vegetable correlate with the heavy metal behaviors in wastewater. So there is correlation. So it means in wet season, the flow increase by the heavy rainfall precipitation. So it can transport or convey more heavy metal to the upstream, from upstream to downstream area. That is a possibility. Yeah. And here is the result of heavy assessment by target hazard quotient and hazard index. We remember this, we compare with 1. If higher than 1, it has problem. If lower than 1, it's okay. So if you see here, the target hazard quotient on the target hazard quotient here, it's the color, except for the gray. Gray is the hazard index. It's the total impact of all element, heavy metal element. So there are no hazard quotient larger than 1. But hazard index on maybe I make mistake here, but only only B and C, not on sampling size. B and C will find higher than 1. This means there is a possibility of health risks from the consumption contaminated vegetable by with heavy metal. And the hazard index in wet season larger than 1. In wet season larger than any sampling size. I did not show here, but that is the fact. And the target cancer rate we find here we only find those in C, size C in wet season, size C and B in wet season. There are many there is the chromium, cadmium, and arsenic have the target cancer rate higher than the threshold. It means it has the possibility of exposure of cancer for these elements in the downstream area, especially in downstream area, clearly. So, summarize. So, vegetable growth in peri-urban farm of facility were contaminated with zinc, lead, cadmium, and zinc. Although the pollution of this heavy metal in irrigation water and farm soil did not pose serious health concerns. So why there is this contradiction phenomenon? Maybe the bioaccumulation in lecture is very high compared with another vegetable. Just the leafy vegetable, they have the capacity to absorb more heavy metal because they grow in very short time, maybe within 1 month. So their bioaccumulation factor is very high. So even there no contamination of heavy metal in soil and water, but it still can be uptake a lot from vegetable like lettuce. And from the PCR analysis, there were we see that there were seasonal effect of untreated municipal wastewater on the heavy metal concentration in irrigation water in dry season, and just in vegetable harvested in wet season. And this trend is not clear in heavy metal concentrate in soil. So for the local population, so when the people consume the vegetable contaminated with heavy metal, this can pose carcinogenic risks for chrome, cadmium, and arsenic, especially in the downstream farm. And during the wet season, because we can see that the wet season had a very high, significantly higher concentration of heavy metal in vegetable than the dry season, and a known carcinogenic risk from the total bioaccumulation on element in the vegetable, irrespective of the season. So the last case study I want to show today is the metal contamination of agricultural fuel around a landfill site in Thailand. So you may know landfill site. I think you understand, you know this place, right? It's quite common in developing cities. And this site is maybe 10 kilometers far from the Bangkok, and it's located in one of the peri-urban area. And these areas form the part that is the agricultural very big, large agricultural production area. So when the local authority decide this place to build a landfill site, it received many complaints from local people, and there's many problems because they concerned about the leakage. I mean the leaches from the landfill site, from the garbage. They have the leaches, and in the leachate may contain heavy metal. So let's see. I did not determine the heavy metal in leachate or in the landfill site, but I determine the heavy metal in the vegetable, soil, and water near the site. But even we only using that result, we can evaluate the effect of the site, the landfill site, to the agricultural area near that. So landfill site, one of the most compatible options in developing countries for disposal of many kind of waste materials, and this site may pose several environmental problems like and groundwater pollution by its leaches is considered to be the most important part. And the leaches from landfill that contain many toxic substance with heavy metal, like heavy metal, have been kept in the stabilization pond. the landfill site in Thailand, I saw that they have the 4 stabilization pond, and with no treatment. They just put it with no treatment, and we hypothesize that when the discharge leachate into the pond could bring the pollutants to the surface and groundwater used for irrigation, used in irrigation for agricultural activity in surrounding area. That means surrounding area of landfill site is agricultural production area. So especially when the rain comes in the wet season, the water from this pond can be seepage from the pond to outside, and that is one of the hazards of this area to agricultural place. and it may cause soil crop and soil contamination. So these studies to investigate the contamination of heavy metal in crop and agricultural soil and irrigation water of agricultural field around the landfill site in Thailand. In addition, the health risk through consumption of vegetable from this field was also assessed. So for your easy to understand, this is the landfill site, and we collect the samples surrounding us. We define the closed area, closed sampling site, and far sampling site based on the distance. There has many canals surrounding this area. Is bring the irrigation water from the closed river to for agricultural activity. And P here, so the stabilization point near to the landfill site, and F is the vegetable farm, and R is the paddy farm. Yeah, I not repeat how to do sampling, and it's the same with the case in Cambodia and Vietnam. And here also we calculate the hazard quotient on the daily intake. That's I did not repeat that one, but apply for Thailand case. So you see here the lies of the permissible maximum level. And so we found more than half and 70% of total number of vegetable sample have zinc and lead concentration higher than standard. It means it have high possibility to contaminate it with zinc and lead. And 54% and 46% of total number of vegetable sample have zinc and lead concentration higher than standard here. And you can see we collect 4 type of vegetable. This only leafy vegetable. You can eat it in raw. The local people eat it raw, in raw, and the basil, kale, lettuce, spinach was collected. Yeah, and even though we found the vegetable was contaminated with zinc and lead, but the level of heavy metal in soil and water did not exceed the standard. That's quite same situation with the case study in Vietnam, right? And copper and zinc in vegetable was significantly higher than those in rice soup. We also check the rice soup, but concentration of arsenic in rice soup was significantly higher than vegetable. Maybe the rice have the property to absorb more arsenic. Acid easily come into the rice than a vegetable. So we had this result. And significant difference between metal contamination in rice soup by distance from landfill site were not found. And here, the concentration of lead and zinc and arsenic in vegetable soil, significantly decreased with distance. This means in close farm had significantly higher lead, zinc, and arsenic concentration than the far one. But zinc is different trend. We did not find the significant difference between zinc, even though the average value still higher in close farm compared to far one. And there is the correlation between the heavy metal in crop and soil in case of cadmium and zinc. So it means the correlation with it means that the the root of the bioaccumulation of these elements can come from the soil in the crop. That's solar trend. And the target hazard quotient value is we find a consistent result that the zinc and have the higher than 1 in Brazil. In farm 1, you remember farm 1 is very close to landfill, and also arsenic. We can see arsenic target hazard quotient of arsenic higher than 1 in many kind of vegetable, and also in the it's not depend on the location of farm, because the arsenic may not come from the landfill. It's the source of arsenic is made from the nature. That's quite common in the Vietnam, also in Cambodia and in Thailand. In soil, they contain many a lot the high concentrated arsenic. So this so that it may not from landfill. So in summary, we see that the vegetable in agricultural land near landfill were contaminated by zinc, cadmium, lead, and arsenic. Although the corresponding soil and water sample were not polluted strongly. And significantly accumulation of zinc in Brazil were found. Meanwhile, there was significantly different concentration of copper, zinc, arsenic between vegetable and rice root. And significantly correlation between vegetable and their corresponding soil were found in investigated method. And the concentration of zinc and copper in vegetable significantly decreased with distance from landfill site, while it was not common in rice root. And a distance dependent decline decreasing was found for lead, zinc, and arsenic in vegetable soil. So it indicates the impact of landfill site. Maybe in the at the sort of contamination, but in somehow the arsenic, as I said, the bigger factor is from the string of the soil at this area, because we can see from THQ result, but we're not sure. But this maybe from the soil heavy metal in soil result, and the potential health risks through consumption of zinc and arsenic contaminated vegetable was confirmed, and the local people should be cautioned about this risk. So I went through the 3 studies, and I have some general conclusion for this 3D study. Thus, in developing city, especially in the suburbs area, the leafy vegetable grow in agricultural land and near landfill or downstream area from city are contaminated with heavy metal like zinc, chromium, lead, cadmium, arsenic. Meanwhile, manganese and nickel concentration in fish collected from tonne sap were not adopted with the standard. The fish were found not so strongly contaminated in this case. It raised a concern about human health risk associated with consuming heavy metal contaminated food. And there was a clear connection between anthropogenic activity and heavy metal concentration in the agricultural system, like domestic wastewater from city in Vietnam case, tonne sap, and also the landfill activity. It have linked the quite strong link with the profile of the occurrence of heavy metal concentration in agricultural system like water, soil, and food. And the cadmium, lead, and chrome, which are known essential elements for plant, were determined from anthropogenic source. So it indicates that the pollution source must be treated. I mean, here I want to clarify this part. This point is in some now the how can I say the urbanization occurs rapidly, so we need the more advanced treatment for the what we release from to the environment, like the greenhouse gas emission, the emission from industrial sector, the wastewater from urban area, and the runoff from agricultural chemical use, something like that. So we should have the strategy to treat it well. Yeah, that's all my presentation today. Thank you for your listening, and it's time to have some discussion, or if you have any unclear points, please ask. Thank you.
Okay, thank you, Dr. Pham.
Yeah.
Okay, and I will a little resume about your lecture. Very nice lecture about the heavy metal.
Yeah.
But in Indonesia, condition is, I think when river contamination with heavy metal is not easy to detect it. But when the manufacture on industrial, the dump of the organic waste, that's the big impact, because the color of river is changed, and then the fish will die, and then they panic. So, so heavy metal is, this is chronic, not acute cause, right? The chronic for a long time. So
for fish, somehow in some way the heavy metal become a acute factor.
Yeah, mostly, and then I've read one few years ago, when people who live in the near of the beach, around of the beach, they have high concentration of heavy metal in the blood.
Oh,
more than of the WHO the standard. I don't know, 3, 4, 5 times more higher. They say it's okay, no problem.
Which kind of plant do you mention? Which kind of plant? That is vegetable or the fruit?
Yeah, some of the health department have survey about the blood in people, not in the animal, blood people.
Ah, I see.
Okay, yeah, that's they don't have the some. They say it's okay, no problem on something. So this is, I think, the problem. But another case, when people inform that in one kind of shell specific in this area, content of heavy metal, all the people is panic.
Oh.
Okay, so they doesn't want it again. So the business become collapse. So now social media have big about how to mix people aware about something. That's in Indonesia. So total daily intake or acceptable daily index, that's very important if we will educate the people, because sorry to say, in most Indonesia, the problem they say it's nothing. That's
Mm,
that's the problem, even of the COVID or something. So we have,
I see.
yeah, we have to like when avian flu, but Indonesia panic. They doesn't want to eat the chicken.
Mm,
We have the Indonesia panic. So cattle is going down. That's like that. So I think it's very interesting. It's in heavy metal contaminant, and then this is we don't have capability to work in this area. But now actually we have group and collaboration with the Kobe University. They work
oh,
one health project. So one group is comprised of the medical science, and then me from the veterinary, and we try. I don't know because because to COVID, not intend to come, so we not discuss. I think that's very interesting. We look at the microbiology, especially in the